This meeting is being recorded.
Right, good afternoon, everyone. Before we start, are there any questions that I can answer? Any concerns, doubts? Something I can clear up? Okay, just out of curiosity from the regulars who were coming in person, who is actually leaving for Thanksgiving and not coming back after? Quite a few. Okay, I assume you're traveling over the weekend probably and taking the exam at home. Okay, will be quite lonely in here. So, if there aren't any general questions about anything in the course, we'll just pick up where we left off yesterday. So what we were doing yesterday, we were looking at how, or different patterns of processing multiple inputs, multiple complex inputs. So just to recap, the first one that we looked at was what we would call a black box traversal, right? So this was really for the cases when we have two complex inputs. Each of them have a recursive template associated with them, but we are only really processing one of them, right? And our job is only choosing which of the inputs we are pulling apart using the template, and which one we are just treating as a black box and carrying around until we get to a case that where we can apply use the black box or the second argument. So when we looked at appending one list to another, and also the reverse of a reverse append. The second pattern that we looked at was processing two complex structures in parallel, where these two structures are assumed to have exactly the same structure, right? We use the list example, and in a list example, them having the same structure means that they have exactly the same length. Right? And using this knowledge, we were basically able to write down a function which simply processes the two arguments in lockstep. If it's a const, do something with the two firsts, and then call recursively using the two rests of the list. Otherwise, if they are both empty, we do something else. Okay. So again, we were processing two elements, but really applying only one template, because we exploited the assumption that if one is empty, the other one needs to be empty too. If one is a const, the other one needs to be a const as well. Okay, so that was the simple case of parallel traversal. The third example was a generalization of that idea. And what we ended up with was taking two complex templates and kind of looking at all the possible combinations of the two templates. We wrote a little table here, a little grid with all the possible combinations, and then we used this grid to actually implement our function. What I wanted to do, and I skipped it yesterday, is actually write out the template for these two combinations. So just like we have a template for a natural number, we have a template for a list of natural numbers. If we combine this, what we get is a template for the combination of these two things. So let me do just that and write out a list nat template. Taking a list, in this case it was a list of strings, so we can use that, and a natural number. And just like in the function, we write out all the possible combinations of each of these data types as two cases. What we get when we combine them is 4 combinations, and here we go. So if we have an empty list and a 0, we might do something, no information provided. If we have an empty list and a positive number, we do something else. Let me just write them out. We have a cons and 0, and finally the cons and a positive. We perform something. Okay, so in these cases, if we kind of look at both of the templates, the empty case and 0 case, both are empty in both templates, so there's really nothing to do here. If we have the empty list and a positive number, right? In the net temple, the template prescribed to have a recursive call on the template function. So what we do here is actually providing or indicating that there might be a recursive call to our combined template function with the number reduced by 1. Okay. By analogy, if we have a cons, we actually have two pieces of information here, right? We have a first of the list of strings that we might want to do something about, and we have a rest of list of string. Call here. And finally, in the third case, we have both a list. We combine the two things from the template. Here we don't change the number. Nat temple on rest LOS and sub 1 n. Okay. So this is what we would call a 2D template or a cross product template. because we take two templates and kind of recombine them together so that we handle all of the possible cases. We still indicate recursive calls if we have a self-reference in there, just like before. In the case where we have a positive, in the second argument over we have a cons, right? And then we just pass along the other argument. We need to. In the case where both of the arguments actually prescribe a recursive call, we just recombine the recursive call into one function. Okay. So this is the template that I should have actually written out before we started implementing get element, but we got there. Let me just. So this was our first version, where we started to implement the get element function by simply listing all the possible combinations, right? This helped us ensure that we were handling all the possible cases that arise from processing these two complex inputs, and these correspond to this template. I just happened to flip the arguments here, but I hope that you can see that it's still the same thing. Here we have the 0 and cons case, which is this one, where we throw away the recursive call and simply return the list LOS. Here we have the positive and cons case, which is this one, where we simply throw away the first and just have the recursive call, which corresponds to the template call over there. And then we decided in both of these cases, so here we didn't have any information, so we just returned false. Here the template would potentially prescribe a recursive call, but if we just had a recursive call, eventually we would cause failure, so we know that in this case we actually don't have the element and can return false. Okay. Okay, so let me just add this here to the or. Okay. So we started with a function that basically follows this template, writing out all the cases and realizing that some of these cases can be joined and some of the conditions can be simplified. We arrived at a function that is much simpler. Okay, it still makes sense to start out with writing out all the cases, and there's a few reasons for this, and one of them is if you write check expects, write out all the possible combinations, try to run the check expects, then Dr. Record will highlight the cases that you missed. Right, which helps you to write exhaustive tests for your function. Once you have those exhaustive tests and you know that you handle all the possible cases, when you simplify and your tests still pass, you can be sure that your function is handling everything correctly. If I just went right here, I might have a single check expect for false, right? I seem to be covering everything, but I might not be necessarily covering all the combinations. Okay. Any questions about this cross-product template and the idea of this exhaustive kind of handling? Okay. So the next example that I want to do is a function that again processes two complex inputs. There's one. We will design a function called list equals which compares two lists returns true if both lists are equal. Okay. That is both lists have the same length and corresponding elements are equivalent. Okay. So I want to write a list equality check, and I want to make it generic. So I want to take a list of X and another list of X and return a Boolean, returning true if the lists are equal, false otherwise. What problem will I run into with this signature, the generic comparison function? Josh?
So in order to check each element of this if they're equal, would you need like an equal dot?
Yeah, so again, we have the same situation that we have had with tests, as Josh points out. We have a generic argument. We don't know what equality to use. So we can again kind of take a shortcut and use equal. But as we explained, equal is really not well suited for this. Just like we had with sets, it worked fine for atomic types and kind of the default types in Dr. Racket. But if our notion of equality is different than what equal implements, it will fail. So the trick that we can use is to simply provide a comparison function with a custom equality predicate. Right, so not only will we give it two lists, but we will give it a equivalence function or an equality check, which for the elements of the given type will return either if they are true or if they are equal or not. Okay, let's do a few examples of this. So. First example, are two empty lists considered equal? Yep. Have the same shape, no elements, nothing to compare. It's definitely true. List 1, 2, 3. 3. These are obviously the same list, so why should return true? And let's do a few false cases. False. Okay, let's try another type. Equals list A, B, C. List A, B, C. And since we have a list of strings, we need to pass in the string equality predicate, and this should return true. If I try this, it should return false. Now, the nice thing about supplying your own equivalence predicate is that you can you have some flexibility in determining what you mean by being equal. So for strings in particular, I can use a different predicate, strings dash CI, which is a case-insensitive comparison operator. In particular, it will return true for strings that only differ in the cases of the letters. So if I use this here, I get true in here using the case-insensitive operator comparison. A few more cases here. Okay. This should roughly cover it. Okay, so I have a function that obviously takes two complex inputs of the same type, right? It's a list of x and a list of x. I cannot use the assumption that both of those lists are equal, because that's one of the things that I'm checking, right? So I can have lists of different lengths, so I cannot use my simple parallel processing template. So what I need to reach for is a cross product template or a 2D template for these lists. So let me just do that. So if I have a list and I have a list, it's two things. I will have the following cases. I either have an empty on one list and a cons on the other one, empty and a cons, which means that, as before, I have 4 cases to cover. Okay. Which means list template. Okay, so let's check how awake you are. How many cases in my cont? Yeah? 4 given by the table. What are the cases? Steven? Empty. Empty. Okay. Second one. Exactly. First one is empty, second one is cons. Let's fill it in later. The third one will be the flip of that, so we have a cons on the first one and then empty on the second one. And then we have a cons on both sides. Okay, what are the bodies of these cases? What about if I have 2 empty ones? Yep. I leave the ellipses, no data included, so we don't know what to do about it yet. What about this case? So first L2, and then the, which one? List, temple, and then rest of L2. Okay. Third case. Okay. 1. Rest L1. L2. L2. Mhm. And the final case.
First L1, first L2, and when you do the recursive call, you can address your
Exactly. So I'll do the first L1, first L2, and then I do my recursive call on rest 1 and rest 2. Okay. So that's my 2D or cross product template for two lists. Let me copy it over here. Okay, is it clear why this template is the way it is? Any questions? Okay, excellent. So if we just follow this template, we can be sure that we are hitting all the possible cases. The prescribed recursive calls might not always make sense, of course, but they suggest how we might be processing the list. So let's implement list equals and we get a list 1, list 2, and then we get the equality predicate. You can use the template that we just defined. And we get to fill in all the possible ellipses. Okay, if both lists are empty, what can I tell about the list? Brendan?
Then you can just return true.
Yeah, two empty lists are empty. I have check specs that verify that. So I can simply say true. Should be good. What about the empty cons case? Josh?
Can we lump the next two cases together?
We'll get there. Let's just fill in the templates.
Return false, what does that mean? This is
Exactly. So if we have an empty list and a cons list that definitely are not the same list, they have a different structure, different length. So what we can do is simply return false in this case. What did it copy here? Okay. Third case. Yeah? Also false. So again, if we have two lists of different shape, eventually we will hit this cons and empty case. We have a list that contains at least one element and an empty list. They cannot be the same. Okay, now the interesting one. What about the case when we have two conses on each side? When we have a cons on each side. Yeah? Exactly. So we need to check if we have two elements in the front of a list. We need to check whether the first two elements are equal using the equality predicate that we got passed in. And then we check the rest of the two lists. Okay. Yay. Let's see. How many typos? Line 166. Which test was that? Sorry? The first one has what? Yeah, but CI should return should return true for that, so we have an error somewhere else. Which one? 165.
Did you pass the predicate? It's a capital C versus a small c. Case.
Yeah, so it says 166, but I'm using a case-insensitive comparison, so that shouldn't be the problem. What were the other suggestions?
Passing the predicate or passing the
Am I passing the predicate? Yes, I am. Should be okay. Oh, very good. Thank you. Awesome. That was a stupid one. Okay, so now we know that our function works. We know that we are hitting all the cases, right? Our check expects are actually checking all the possible combinations in here. So now we can simplify the case. Right? The point here is to make sure that you are hitting all the possible cases, and the template, the cross-product template, helps you with that. So what can we do with this? What can we get rid of? And collapse, simplify. Yeah?
For the middle two,
Uh-huh.
if we just remove and then say otherwise it's not the first and fourth case.
Exactly. So these two cases are the cases, basically the check when we don't have two empty lists, or we don't have two lists that have a cons. So if we just let these two cases handle the two cases where we potentially can have a true result, and simply let me save the original one. We can collapse them. And return false as an else case. Okay. The drill here is, once we write out all the possible cases and we are sure that we are handling everything correctly, then it's time to start looking for how we can optimize and simplify our code. Okay. Any other simplifications? Yeah? No. Yeah, I think it might be actually. Let me see. It actually is. So I don't know what it's defined as, what equality it implements, but yeah, that was the nasty error. Okay, so it is a predefined one. Any other questions or any other possibilities of how to simplify this code? Okay, not really. So again, the take-home message here is make sure you are handling all your possible cases and optimize after. Okay. It seems like almost every famous computer scientist has a quote about how you shouldn't optimize before you know that your code is correct. There's one that says premature optimization is the root of all evil. Okay, and that's kind of the message here as well. It's like we know, based on our experience, that we might be able to collapse these two cases and avoid them, but it's still a good exercise to write them out, make sure that my check expecs actually cover all of the cases, and only start simplifying and fiddling around with the code, seeing how I can make it a little bit more clever after I'm sure that I'm hitting everything. Okay. Any questions about the list cross template or? Okay, so one thing that I also wanted to mention here is, let me actually do this on the template here. Where did I write it out here? So in the second kind of traversal where we processed lists in parallel and we used the assumption that both of the lists have the same length, right? We only used the template of one of the lists, right? And we can justify the use of that template just by taking this template, remembering the assumption that both lists have to be of equal length and simplifying the template. Because if we go through these cases, right, we can check whether this situation satisfies our assumption. So if we have two lists, if L1 and L2 are of the same length, can they be both empty? The answer is yes, so this is the one that we keep. The next two cases violate that assumption. So if we have one empty list and a cons list, they cannot be the same length. So this violates our assumption, which means that we can simply remove them just by using this assumption. Right? And then finally we have these two cases where we have empty and cons, and the way we arrive at the NM template that we originally wrote for this lockstep processing is, well, we say that both of them have the same length, which means that if L1 is empty, then L2 is also empty, right? So we are basically checking the same thing. So if we use this assumption, we can simplify the conjunction here to a single one, because empty L1 automatically implies empty L2, and the same case, cons L1 implies cons L2 just based on the assumption that they have the same length, and we arrive at the original template that we used in our parallel kind of lockstep traversal. Okay. So just to show how the second kind of traversal that we use is really just a special case of this more general processing. Okay. So we saw how we can process a list in parallel. So let's now do a long and tedious exercise with doing same kind of thing for trees. All right. We have a funny kind of tree that contains symbols. It's not really a binary tree because it contains a branch that just branches in one direction. Okay, so that's like a list cons. And we have a fork which actually branches into two directions. So it's a similar data type to, I think, where did we have it? I think it was the tournament tree example that we used at the beginning. So let me do some examples. Simplest kind of tree is one that just contains a symbol. Then we can have a single branch containing a symbol again, and another tree. Or we can have a fork which contains some symbol and then contains two further subtrees. Okay, simple data type. Let me write out the template for this one quickly. We have three cases here. You either have a symbol atomic, or we have a branch where we have the value, so we can make use of that branch value of tree, and we have a recursive call to the template, which branch next tree. And we have the final case, which is a fork, which again contains a value, but branches twice, which means that we have a double call to our tree template. Left tree, process the left one, and we process the right one. And we're done. Okay, should be relatively familiar to you. Nothing surprising here. Okay, now I want to write a function that processes two trees at the same time. Okay, I won't tell you what I'm doing with that function, but because I'm taking two trees and returning something, I might have to use a cross template. How many cases in a cross template for two trees? Yeah? So it will be 9. We'll get there. So we have two trees, right? Each of them has 3 cases. Either it's a symbol, or it's a branch, or it's a fork, not dork, fork, symbol, branch, fork, which means we have 1, 2, 3, 4, 5, 6, 7, 8, 9 possible cases. Okay, this one will be fun to write out. Better get started. Okay, so tree temple. We have 2 trees. We have a con. We established that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 cases. All right. If we just follow the table and write them out, so we have symbol tree 1, tree 2, then we might have a branch on the right hand side and a fork. Then we have a branch on the right hand side and a symbol on the branch on the left hand side and a symbol on the right hand side. Branch, fork, and finally all the fork combinations, fork, fork symbol, fork branch, and fork, fork. Okay. All the possible cases that can arise from combining these two trees. Again, just a cross product of all the cases. Okay. What are the bodies? First one. Yeah? Leave ellipses. Second one. Yeah?
Branch dash value tree.
Okay, so I know that I have some info with my second tree since it's a branch, so I do value tree 2,
Ellipses tree
tree template,
tree
tree
one.
1,
Branch dash next.
and then branch dash next tree 2. Simple fork. Yeah?
Do a similar kind of thing when you have the tree template on 2, or you have 4 left, 4 right. All the tree templates.
Okay, so the first thing that we have is that we have a value on tree 2 in a fork, and then we have 2 calls because we have a left subtree and a right subtree. Left tree 2 and a fork right on tree 2. Okay, branch and symbol. Yeah?
Branch value tree 1.
Okay, so I have branch value tree 1, tree temple,
Branch dash next tree 1.
next tree 1, followed by tree 2. Okay, branch. Yeah.
Branch value tree 1.
Okay, we have branch value tree 1,
Then
then branch
branch value tree 2.
value tree 2,
Then tree template. We're using branch dash next for both tree 1 and tree 2.
branch next tree 1, next tree 2. That's one of the more interesting cases. Okay, 4 more to go. Brennan?
So you have the branch value of tree 1.
Tree 1.
You want to like keep all the recursive calls towards the end.
Let's keep them towards the end.
And then it'd be fork value of tree 2.
Value of tree 2.
Then you would have tree template of branch next tree 1. Fork left
Huh?
2. And then you do the same thing, but with fork right 3.
2. No, that was tree 1. Fork right of tree 2. Right. Okay. the last three. Yeah, they want to alternate. Okay. Fork dash value tree 1. Tree template fork left tree 1 and tree 2. Tree temple fork right tree 1 tree 2. Okay, fork branch. Yeah. Fork dash value tree 1 branch dash value tree 2 tree temple left tree 1 next tree 2. Let me right tree 2 and the last one. Yeah, Brendan?
So you want to access both the fork values from tree 1 and tree 2?
1 fork value tree 2.
And then you're going to call the tree template on the fork left tree 1, fork left tree 2.
2.
And you're going to call the tree template on the fork right, no, fork left tree 1 again, and then fork right of tree 2.
Okay.
And another one where you call it the fork right tree 1 and fork left tree 2.
And
One last one where you call it on the fork right of fork.
okay. Okay. Thanks. Yeah.
So like, is there an easier way to do all this? Like, what if we have like trees with like 4 branches or 5 branches? Like, we're just gonna integrate like just the number of branches you get, or cases.
Yeah, of course. This is what you will be asked to do in the assignment. No, the reason why we did is like this is obviously ridiculous, right? To write out. But it's still a good exercise to actually think through all the cases and all the possible combinations. This is like the most general template or the most general function that you could think of processing the trees. Okay, you cover all of the bases. And in practice, in particular, since our goal is still some sort of parallel processing, in practice, even if we write out this template, we actually forget about the 2 combination cases. But yes, if we follow it to the T, we actually combine all of these things. Okay, so kind of the message here is that up to now we've been working with templates where it was actually reasonable to write them down and then copy paste them and so on. But when we start processing more complex data and we want to write out the full template, you actually spend more time trying to write down the template than writing probably 5 functions over the data type, okay? But it's still a good exercise to think about that. What are all the possible combinations? Okay. I would argue that writing all this out is not very productive. what might be productive is writing out all the possible combinations that might arise and thinking about them. Okay, especially if while you're not used to processing multiple things, right? As you become more mature and more experienced programmers, you will go to solutions right away. But this, writing out all the combinations, even if you don't write out the bodies, will help you at least, will help you think about what cases you want to cover, what cases you want to cover in your test. Do you have enough examples to cover all of these cases? Okay, so now that we wrote out all this and spent some very productive time trying to write this out, let's write a tree comparison function that simply compares two trees recursively and returns a Boolean, right? So one in particular, if we have two of the same symbols, want to return true. Different symbols, different things. Etc. Tree 2 true, tree 2 3 false. And what was the example? Is it left? We're good again. Left. Okay. So it should be some examples. Okay. Now, if I start with the complete thing, this humongous monster that we just created, and go case by case. I want to return true if I have the same tree, right? First case, two symbols. When are these trees equal? Brennan?
Check if like they were simple equal
Symbol equal, tree 1, tree 2. If they are the same symbol, then we're good. Okay, now we have all these fun cases where we have different shapes, right? So we know that if we have a symbol and a branch, they cannot be the same tree. If we have a symbol and a fork, they cannot be the same tree. If we have a branch and a symbol, they cannot be the same tree. If we have a branch and a branch, yeah? Symbol equal, compare the two values, which are symbols as well. And then, what do I do with the rest? Yeah, I just call the function recursively. Okay. The boring case is if I have a branch and a fork, it obviously cannot be the same. If I have a fork and a symbol, cannot be the same. If I have a fork and a branch, cannot be the same. If I have a fork and a fork, Brennan?
With check, because the fork values are simple, not equal, not.
Uh-huh. So if the two values are the same,
You just make sure that all of those are also just
and the left subtrees are the same, we are not cross comparing the subtrees, and the right subtrees are the same, then we're good. Brennan?
Do you ever need to like cross compare stuff?
Yeah, so usually that's what was my point. Like it's very rare, and I don't think I ever wrote a function that would need to like cross process those two things. And what we are aiming for here is really doing parallel processing. These other cases sometimes they do arise, but like kind of taking two trees apart and somehow doing something across is usually not the case. Josh, I think you had a.
It was the same question. Why do we get rid of the no to recursive parallels?
Yeah. So in here, right, we are not. Would this make sense in this case? Do we need to ensure that the left subtree is the same as the right subtree of the other one and vice versa? Right? It doesn't quite make sense for equality. And in practice, it's, yeah, I cannot think of an example where this would actually make sense in general. Okay. So that's why we can easily get rid of that, especially in this case. And in general, in the template, it's just not a case that is worth thinking about much. It basically never arises with data like this. Okay, let me try to run this, see how many typos I introduced. Wow. Okay. And I kind of hope that you see by running this test, these are all the cases that my check specs don't cover, right? Basically, I can see that that I didn't handle some check specs. I'm not actually exhaustively testing my function. Now, if I just take this and we simplify it, leave this in here. Okay, so we have all these cases that are false, which we can again collapse and replace with a single else branch at the end, right? Because all of our cases, that's nice actually about doing the cross product, all of our cases are mutually exclusive, so anything that doesn't fit we can simply replace with an else. Right? So I didn't write a good test case for my two forks, so that's another problem. But my else case is tested, right? And now I don't see all the cases that I didn't hit in my test. So there's some value in actually trying to write it out. Let the coverage kind of feedback lead the way and tell you when you need to reinsert anything. But we can simplify everything to these cases, right? They just check basically what they say, that the two trees have to always have the same shape. They always have to be a symbol, always has to be two branches, always has to be two forks. Otherwise, it's false by default. Okay. Any questions about this course product? Yeah.
When you're writing functions that use templates,
Uh huh.
do you copy paste this template and then put in the false cases where it's not the same, and then delete them afterwards? Or do you just start off with this, focus
So at this point, I would recommend writing out all the possible combinations. Okay, especially like if it's feasible. Like if you have 4 cases in each and you suddenly need to write out 16 cases, then you might want to think about how to simplify that. But it's a worthwhile exercise because then you know you cover everything. Okay, you don't need to write out the whole template before you write the function. Just write out all the possible combinations. That's kind of the message here. Start by writing all the possible combinations of your data. Make sure that you cover them well, that you have correct code for each one, and then simplify once you're done with that. Okay. Any other questions? Okay. So thanks in taking part in this fun little exercise. There's a question. Are you able to post this code on Piazza? Yes, I will post the code to Piazza hopefully tonight. Okay. All right. If there's nothing more, then thanks for coming. Have a good weekend. Those of you who are traveling, safe travels. Stay safe and stay healthy. And I'll see you around online.